We'll proceed on integral calculus. So we are seeing now in 2D, means for the line. Now we'll see 3D, and that too for the surface. So that is the idea, that we'll see proceed on the from the line equation we'll proceed to the surface. So uh, integration is nothing but addition. So this is what we have been seeing. So if we need to add something, then whatever we need to add, we have to come with a formula. So we have to get we have to uh, get a formula, and then based upon the formula we get the area, and this is how we calculate the addition. So integration is nothing but it's a simple addition, where addition is calculated through area. Simple, right? Means if I have example, we have given like a person, he is working and he is collecting 5 kilometer per hour. Every hour he is walking and 5 kilometer he is able to collect. At the end of 5 hours, how many kilometers he has collected? So if I draw a graph, so if I draw a graph, okay, if this is x-axis, then person is okay. If this is x-axis, then person is walking, okay, constantly. Oh, okay, this is nice. So person, this is x-axis, and person is walking parallel to the x-axis. This is independent component, and this is time. Okay. So there is a first hour, second hour, third hour, fourth hour, fifth hour, and he is collecting parallel to the x-axis. Means that every hour the collection is vertical. If x-axis is this, then this is y-axis. We are talking about everything in a single plane. In a single plane. If this is x-axis, if this is x-axis, then this is y-axis. If that is true, then we are talking about when dependent and independent component, they are in same plane. So time, that is x-axis, is independent component, and the the speed at which he is walking, or number of kilometers collecting per hour, that is the speed only. So number of kilometer per hour is the vertical. Now if person is this, if this is time and this is how he is walking, means this is parallel to the time. Parallel to the time is a sense that it is constant. So he is collecting 5 kilometer every hour constant. So the graph what we draw, if this is x-axis, then parallel to x-axis we draw the line. So then this is the height, then this much he is walking per hour. So if he is collecting now, instead of walking, he is collecting per hour. Better that if we use the term that stick to the basics of mathematics. So mathematics basics lies in addition. So collection is like addition. So person is collecting 5 kilometer per hour. Then how much net collection at the end of 5 hours? So at the end of 5 hours means 5, 5, 5, 5, 5. 5 times if I do, then it will become 25. Or 5 into 5, then 25. Or if it is this height is 5 from the x-axis, this is x-axis, and this is the height, then this height of this line is 5, then he is collecting 5 kilometer every hour. Then the area, this is the collection per hour, this is x-axis, then this is, and this is more or less, this plane is the is the area for which if bottom is x-axis and top he is walking, and from this point to this point is 5 hours, then pull this one down the line. From this line to down the line is rectangle. If I calculate the area of rectangle, then it will become 5 into 5. So that is the kilometer he has taken. This is what we have seen. So area, if we calculate, so equation of this line is 5 constant. So 5 into 5 is 25. So 25 he has traveled. Okay. Now area, calculation of the area, we also call it integration. If I say, if this is t, if I say 5 dt, integrate 5 into dt, integrate. If I do like this, then I am trying to calculate 5 into t. Okay, so 5 is a constant. I can take it out and I am integrating dt. If I am integrating dt, means I am integrating t to the power 0 dt. If t to the power 0 dt, then integration of t to the power 0 is t to the power n plus 1 n by n minus n by n plus 1. This is what we have seen in the last session. So t to the power n plus 1 is t to the power 1 by 1. So integration comes as t. 5 we have taken out, so 5 into t. Total time is 5. 5 into 5, 25. This is what is the addition. Now equation of the line is like this. From origin it starts from origin it starts and it goes like this. This is x square. Can you see? Okay, so bottom line is x-axis, then it goes like this. Okay, it goes like this. So this is typically x square. Okay, so what I'm trying to say is that if it is x-axis, time axis, then if it is like this, then this is x square or t square. If independent component is t, then collection is in equation of t square. Earlier collection was in equation of only 5 constant. Every time slab, every 1 hour he is collecting 5 kilometers constant. Now it is t square. T square in the sense that any time t, the net collection is t square. Okay, or this is in terms of collection. Let's say collection per hour. Okay, that is t square. Again, so if I say if it is at time 1 hour, then at that moment his speed is 1 kilometer per hour. So he is collecting at that moment 1 kilometer per hour. If time equal to 2, at that moment he is collecting 4 kilometer per hour. At time equal to 3, at that moment he is collecting 9 kilometer per hour. At time 4, at time 5, at that moment he is collecting 25 kilometer per hour. So his speed is 25. That is t square. But in earlier case, if it is x-axis and this is the collection per hour, at time equal to 1 hour, his collection is 5 kilometer per hour. At time equal to 2, collection is 5 kilometer per hour. At time equal to 3, collection is 5 kilometer per hour. At time equal to 4, 5, collection is 5 kilometer per hour. At every moment, 5 kilometer per hour. So the equation is 5. So 5 dt integration. Now it is t square. So t square dt integration. So t to the power 2 means its integration will be t to the power 3 by 3. T to the power n is t to the power n plus 1 by n plus 1. So it will come as t to the power 3 by 3. How much he has collected at the end of 5 hours? T to the power 5 to the power 3. 25 into 5, 125 by 3. That is, he has collected around, I mean, it can be calculated. That will come as 4 and 1. Okay. So and then I believe it will as around 7. So 125 means 120 is 4 and then 5 if I see by 3, then 1 remaining is 2, then around 7. So it will come as around 41, okay, point 7 or something like that. So that much is the kilometer he has collected, or 125 by 3. So that much kilometer he has collected. Okay. So integration is nothing but addition only. But integration is a way to calculate the addition through calculating the area, where the dependent component, if this is time and whatever the graph we are drawing, so this is independent, that is dependent. So dependent components equation we have to find some. Okay, how it is varying, that equation is required. That equation should be rate of change. Okay, if I have rate of change as dependent component, dependent component, then area is total collection. So if rate of collection, how much is collection happening per independent unit, independent in time, so per independent per hour, so how much collection is happening per independent unit, if that is the y axis, then if I get the area, then it is how much is the net collection, that is the area. That is calculus. Integration. So integration is if dependent component is rate of collection per unit of the independent component. Rate of the kilometer that is collected per unit of the independent component is R per hour. Rate of collection of kilometer per hour. If that equation, if I know as dependent component to the independent component, then underneath if I calculate the area, then that is the total sum, total collection. So that is another way of calculating the addition, that is integration. So straightforward, right? Means integration is nothing but calculate one way, another way to calculate the addition, where the whatever we are getting, collecting per unit time is in a way is kind of is a function of independent component through some equation. If I know the equation, then I know the graph. If I know the graph, then from a limit one point to another point down the line, I know the area. If I know the area, then I have calculated the addition. Multiplication is also nothing but it's addition. So addition, multiplication, integration, all are addition. So integration is a way to calculate the addition through the area. That's it. Now, area is calculated through the equation, where equation is nothing but rate of collection per independent unit per unit in independent component. So, like if he is collecting 5 kilometer per hour, means 5 kilometer per hour is dependent component, 5 kilometer dependent component per independent component, that is per hour. Then we have the area, and finally that is the integration. But this what we are talking about is single line integration. What about surface 3D? Okay. Now suppose that we had only one independent component. Okay. So generally people are saying that I should draw on a board, and so that things will be clear. Tell me one thing. That is, these are the 3D model how I can draw in the board. If I take the board and if I draw all the movement like this, the way I'm showing, then it will take one day for 5 minutes. Keep drawing it like this, then this, then this, then this, then this, then this. So not possible. So multivariate calculus has to be shown like this one. There is only one. Now calculus is like that. So multivariate calculus. Now we'll enter into integration of the multivariate. Now, if this is xy plane, if this is xy plane and this is x-axis and this is y-axis, this is y-axis and this is x-axis. Now, this is x-axis or this is x-axis, this is y-axis. This is xy plane. This is xy plane. If this is xy plane, then fxy, okay, the function over xy is vertical component z. Earlier, this is this is x-axis. Function over x-axis is fx, that is y. So that is vertical. Now everything was in a single plane. Now there was only one independent component. Now there are two independent components. One independent component is x-axis, another independent component is y-axis. This is one independent component, this is one independent component. Or like this, if I say from my side, this is one independent component, this is one independent component. Okay. Now it forms xy plane. If this is xy plane, the function over xy is fxy. Then fxy is vertical. At any point x and y, at any point x comma y, what is fxy? Fxy is the vertical, that is z. So z equal to fxy. Z can be 1 plus x into y. Z can be x square plus y square. If it is x square and y square, then this is paraboloid. If it is x square plus y square square root, then it is cone. Okay, it is cone here. Okay, like that. If it is like that way, so it can be cone, it can be paraboloid, it can be cylinder. So these are the z that is dependent upon the fxy. Fxy is a function over x comma y, where x comma y is all the points on this plane. All the points on the plane. Each point can be referred as xy. For each xy, there is fxy. For that fxy, we call it z. So z equal to fxy. If z equal to fxy means that vertical component. This is 3D, where two independent components are there, x and y, like this. So this is a kind of one kind of shape, and this shape is above this plane. This shape is above this plane. This is the plane. This is the plane. Then this is 3D. This is 3D. Now this 3D, at each point in xy, that is on this plane, there is a height we can see. So from here the 3D starts and it goes like this and it ends here. So this is typical 3D. If this is 3D, then 3D is, then for each x comma y there is a height, that is z value. This is 3D. Okay, now we have to find, earlier we find area, we remember it. Means if I have x-axis and y-axis and things were in single plane. So if this is t, then this is y. Then y equal to ft. Everything in single plane. If I want to do addition, then I had to calculate the area. Here, if I want to do addition, then I have to calculate the full volume. So earlier, the height, we were calculating height into base was the area. Now also, height into base is the volume. This base is area. Earlier the base was line, height was line. Now height is line, but base is area. So area into height is volume, because area itself is two dimension. Area itself is two dimension. So area into height is volume. Okay. Now consider that I have this 3D. What is the volume of this 3D? Pretty simple, right? What is the volume of this 3D? Okay. Now this 3D has set of xy in the xy plane. Now the xy plane, the area in the xy plane, what it is covering, that area into height is the volume. Straightforward. Whatever the area we have down the line in xy plane into height is volume, but height is not constant. Height is in some equation. Suppose height is 1 plus x into y. Height is 1 into x into y. And down the line, what we are calculating now, suppose it is a rectangle. Okay, suppose height is 1 plus x into y, and down the line x has limit from 0 to 3 and y has limit from 0 to 3. Okay, so consider this point as origin. If this is the origin, then 0 to 3 here and 0 to 3 half. So half, this area is the base. On this base, it will come as one quadrant of the four quadrants. So this base, if this is the base on which 3D model sits, what is the volume of 3D model? Okay, so let's not concentrate on the equation. How we can? Okay, what we did in 2D. So that's why mathematics is a thing that you have to understand step by step. Higher steps are sitting on lower steps. There the amount what they carry is high. Amount lower is containing is low. So it is easy to understand. But the concept is same. Now, if I am saying that if I am trying to calculate the area where the base is a line and then there is a height, then a height into base is the area. Now, area is, can we see, this is a plane. Plane has no width. Area has no width. Okay, in 3D, area has no width. Area has base, area has height. If I multiply base into height, we get the area. But this width wise, it has no width. It is tends to 0. Can you catch it? What I'm trying to say? Suppose that suppose that this is the full XY plane, and whatever 3D model we showed that covers the full plane. So 3D model is big. So this 3D model, what we are saying, it covers full plane. Okay. Now if it covers full plane, then can we see this? If this is x-axis and this is z-axis, then there is a xz plane. If this is x-axis, then there is a xz plane. If this is x-axis, then again there is xz plane. If this is y-axis, then there is a yz plane. If this is y-axis, then there is a yz plane. If this is y-axis, then there is a yz plane. Y-axis is independent, z is dependent. Y is independent, z is independent. Y is independent, z is dependent. X is independent, z is dependent. X is independent, z is independent. X is independent, z is independent. So many surfaces are there. In the earlier case, we consider this as a plane and this is x-axis and this is y-axis. Y-axis is dependent and x-axis is independent. Calculation were happening in single plane, in a line. So if this is independent, this is dependent. That's it. X-axis and y-axis. So things came as an area where the thickness is tends to 0. Only one plane story. Now this is dual plane story. I mean, it's a 3D story where the independent components are two. X-axis is independent y-axis is independent, whereas z is dependent. But we are committed to repeat same story because that's what we know. One independent and one dependent. What we can do? So if this is x-axis, then z is dependent. This is independent and z. So this we have found xz plane. And then we have found yz plane where one is dependent and one is independent. You will not get this kind of explanation in any of the books. You can find it. Anyway, okay, how we can understand the 3D model through 2D model. Nowhere it is available. Okay. Now, since I know if it is x-axis and this is z-axis, can we calculate the area? If I know this is x-axis and this is z-axis and this is z-axis, this is x-axis, this is xz plane, the way we talked earlier, xy. Okay, in the beginning case, yesterday means in the previous session. So if this is x-axis, then it is z-axis. Then this is the equation. The equation is 1 plus x into y. Can we calculate area of this xz plane? If I calculate the area of the xz plane, then one area is calculated. Now, now for all xz plane, we have calculated the area if it is in function of y. Okay, if I calculate the area in xz plane and it comes as constant, then that is another story. If I am calculating the area in xz plane and if it is function of y, then at each y, this is y, this is y, this is this is y. You will not get this expression anywhere. This is y and this is x. This is x and this is y. Now, xz plane, the area at any y, at now we have so many y. Can we see this y, this y? So xz plane we are proceeding. So if I am talking at this xz plane, then it is at one particular y. If I am talking about this xz plane, then it is at particular y. If I am talking about this xz plane, it is at particular y. If I calculate area at this xz plane, then it is calculated at the y, particular y. Okay, then this xz plane, the area what we will calculate, that will be function of y only because we are calculating for a y typically. Now, whatever the area we have calculated, if I have that area as a value, area as a single value at a particular y, then those single value, if I draw in this direction, then that is nothing but another surface. Are you getting it? If I am calculating xz plane, xz plane is the area and that area is a number that is a function of y at particular y. Okay, if I know the y, I can substitute the y value and that particular y, I know what is the xz area. Getting it, right? So if I calculate xz plane area and area is a function in y and I know the y at particular y, if I substitute the y value with that value at that y, because there are so many xz plane, right? One xz plane, two xz plane, three xz plane, four xz plane, fifth, six, seven. There are n number of xz plane at each y. So if I substitute the y value in the xz plane in area, then at that y, what is the area we calculate. Okay, now if I multiply that area with the y, then area into y we get. Okay, area into y is nothing but volume. Area into one more component is volume. So first we calculated area along xz plane at particular y. Now if I integrate along the y whatever we received, then we get for the full volume. Simple. So if I say that fxy is the dependent variable over x and y, then fxy dx, what we calculate, that is the area. Fxy dx is the area at any y. Now, if I have fxy dx, that is the area of two dimensional at any y, then if we have calculated the whatever we have calculated, we integrate again with the dy. So fxy dx is the area along xz plane. Then whatever we calculated, then again we integrate it with dy, then we get the full volume. Like in two dimension, we if it is t and this is ft, then if I integrate ft over t, then I get the area. Like that, if I have x and if I integrate x, if I integrate function over x or function over xy along z axis, that is xz plane, then I integrate fxz dx, fxy dx. Whatever we get, that is the area along the xz plane at particular y. Whatever we get, again if we integrate along y axis, then all the area we get the volume. If I have in 2D, if I have a x-axis, and I have a line equation, if I integrate over it, we calculate the area. If I have a area and I integrate over it, then I get the volume. Okay, so in 2D, if I have a line, if I have an independent component, that is x-axis or time, okay, if this is independent component and this is dependent component, that is ft, if this is t-axis, this is ft. If I integrate line t-axis ft from one point to other point, if I integrate from one point to one point, it becomes area. If I have area xz, if I integrate it from one point to another point in y direction, area becomes volume. Okay, so what is required? Required is in xz plane. First you calculate the area at particular y. Whatever area you get, then that area you integrate it over y. Then area into y becomes volume. Here in 2D, the line into height became area. Here the area into height or y-axis becomes the volume. This is one way. Another way is, first you calculate yz plane. This is yz plane. So one area, another area, another area, another area. You have infinite areas, that is vertically it is calculated. Now this is along x-axis. At each x, you have one area. So area into x is volume. Okay. So area can be seen like this. So if I see, okay, so this is x-axis and this is y-axis, and this is x-axis. Okay, now each axis we have a yz plane. This is one yz plane, another yz plane, another yz plane, another yz plane, another yz plane. So many yz planes are there. Okay, if I integrate all the yz planes along x-axis, I get the volume. Or 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 one yz plane, one yz plane, one yz plane, one yz plane. There are so many yz planes. There are so many YZ planes. Okay. Now each YZ plane is at one particular Y. If I integrate YZ plane over all the Y, so area into one more length is the volume. What is prerequisite here? So whatever, if I have XZ plane, so many XZ plane at particular Y, then typically XZ plane will be function of the Y. Okay, so the boundaries. So if I'm integrating the area XZ plane area, so it has, if this is the area we are calculating, so this is XZ plane. This is XZ plane. The left side is the left boundary and right side is the right boundary. Left side is the left boundary and right side is the right boundary. So when we integrate the left boundary and right boundary, that we have to provide. So this provision typically it will happen with function of Y. If I get that, then whatever area we are calculating, it will come as function of Y. X will diminish. And then whatever area we get, we have to integrate over Y. Then we get the Y. Or we have to calculate, for each X, we have to calculate the YZ plane. Now, the limit for the YZ plane will be variation of X. Now, once we get that, for full X, I have to integrate it again. So, area into X will become volume. Both are same. Both are calculating the same one. So, we will proceed on this. Okay, we will proceed on this and we'll take some example. Then we'll carry on with the approximation. Okay, that is the basic concept of integration. I should have explained it before, but this was required so that continuity would be maintained. So we'll take one example of this, that how we calculate the volume in real life with area into, first we calculate dx and then dy, or first we calculate dy then dx, and that we calculate the volume. So we'll take example, then we'll explain the approximation case in the integration, that is also considered as base for the integration. I hope you have enjoyed it, but things will looks complex, but the same story I would repeat, that mathematics is step by step. So if we understand the most basic step, then it is one ever one ever one. But it will be like a pyramid. So base will be simple, like addition is simple, right? But it will be like pyramid. Things will sit upon it. Okay, I mean pyramid is like this. Okay, sorry. So pyramid is like this. You can think it as a tilted pyramid. So as you go along, then things will become, things will sit on top of it, but the quantity will become more. So it requires more kind of, you can say, that your orthographic view. Okay, so that is the concept. But anyway, we will proceed and on this, and we'll take as many sessions as possible so that it will be repetitively, we will repeat many things so that things will be quite clear. Okay, please consider.